Okay, today we get to define the definite integral of a function. In the last section, we were approximating areas under a curve. And we did this by adding up areas of rectangles that were sort of straightened out versions of that area under a curve. So it looked kind of like this. You have that curve and we want the area under it, so we kind of approximate it with these rectangles. And we did left or right endpoints last time, but as you see in this picture, you could use any point in the x part of the rectangle, in the horizontal part of the rectangle, that subinterval, to get the height of the rectangle. So you pick any point in there and then you follow it up till it hits the function, and that's how high you draw that rectangle. And then the next one you pick another point, follow it up, and that's how high you draw that rectangle. And the notation for the point you pick in the first interval is x1 star, and in the second interval it's x2 star, and so on. So in the ith rectangle, the point you pick to get the height is the xi star, and that means the height is f of xi star. So to get closer and closer to the actual area, right, this is an approximation, to get closer and closer to the actual area, we'll use more and more rectangles. If you're fitting more of them in, they're going to be narrower and narrower. And that width, remember, is the total width of the whole section you're doing over how many rectangles you are using. So that's delta x, the width of a rectangle. And so when we do this, we get this horrible looking definition. If f is a function defined on the interval from x equals a to x equals b, we're going to split this interval into n pieces, n subintervals of equal width. That's the delta x, b minus a over how many rectangles. And we pick a sample point in each subinterval or rectangles area. That is, x1 star is in the first interval, x2 star is in the second, and so on. Then we're going to make a definition, the definite integral of f from a to b. The definite integral, which we write with this elongated s with an a on the bottom and a b on the top, of the function, we'll talk about what dx means in a bit, this definite integral equals the limit as n approaches infinity of this thing. What is this thing? Well, in this thing, you see some f of xi star times delta x. Remember, that's the height times the width of each rectangle. So each of those things is an area of a rectangle. And then what's next to that is a sigma, a Greek letter sigma. It's a capital sigma. And it means add these things up. So it's a summation or a sum. And it means add up all the stuff on the right, that is, add up the areas of the rectangles from I equals 1 on bottom to n on top. That means you put in I equals 1 and get the area of that rectangle 1, plus put in I equals 2, and that's the area of rectangle 2, plus you put in I equals 3, and so on, and you stop after you put in I equals n. So for each rectangle, we're adding up its area. That's all that means. But now we're letting n go to infinity. That means we do this for 5 rectangles, maybe n is 5, we get some number. We do it for 10 rectangles, n is 10, we get a different number. More and more and more rectangles, so we're getting closer and closer approximations to the actual area. And as this limit goes to infinity, as n goes to infinity, we should be getting the exact area under the curve. So this definite integral is producing the area under the graph, as we saw last time. As long as the limit exists, right? If the limit doesn't exist, then there's no such thing as the definite integral of that function. If the limit exists, we say the function is integrable. Means it has an integral. This thing where you add up the limits, the areas of rectangles, is called a Riemann sum for the function. Riemann was a mathematician who invented this, essentially, or at least systematized it in the 1800s. So this part of calculus was not invented by Newton and Leibniz like derivatives were. This is more recent, and so this is a Riemann sum named after him. And again, I want to emphasize that this limit, more and more rectangles, might not exist. If it does exist, the function is called integrable. If it doesn't exist, the function is not integrable, which means it doesn't have an integral. So, to summarize, this thing, the definite integral, gives us the area under the graph of the function from x equals a to b. Now that assumes that the function is positive. In all the pictures I've drawn so far, f of x has been positive. It's been above the x-axis. But if f of x is negative at some points, then that f of xi thing could be a negative number. So delta x times f of xi isn't positive. It's a negative number. And areas aren't negative, so that's not an area. So what is it? We're adding up these things. If f is positive, they're areas. If f is negative, I don't know. We're adding them up and taking a limit. So what is that definite integral? Well, it's related to area. The Riemann sum, which looks like this, it is an approximation not to the total area, but to the net area that you see here. That is, you're adding up the areas of rectangles, except if they're below the x-axis, you make them negative. You make the area negative and add that up. So you're adding the areas above the x-axis and subtracting the areas below the x-axis. Okay. So that the Riemann sum is an approximation to the net area. The definite integral then is exactly equal to the net area between the curve and the x-axis from x equals a to x equals b. That is, in the second picture, you add up the blue areas and then subtract the orange area, and that would give you the definite integral of f of x between x equals a and x equals b. Okay, I want to mention this thing called dummy variables, and that's just to notice that this integral we've been talking about, the definite integral of f between a and b, would be the same if instead of x being the variable I was thinking about, I labeled that horizontal axis t, or u, or anything else. So, in some sense, the variable you're using in the function doesn't matter when you compute the definite integral. You get the same answer, the same net area, no matter what that variable is, and that's why it's called a dummy variable. However, do notice that the dummy variable, the variable, also appears in this du thing. So what does that du, dt, dx tell you? Well, it comes from the delta x, or delta t, or delta whatever, the width of the rectangles. Remember, the Riemann sum, all of them, was f of something times delta x. And so when we make more and more rectangles, those widths get smaller and smaller and smaller. The delta x's get smaller and smaller. And so in the limit, we write it as dx instead of delta x. It's sort of an infinitesimally small width. You don't really need to worry about, though. Mostly, it will just tell you what variable to integrate with respect to. That is, if you see dx, then you're thinking of x as the variable to take the integral of. If you see dt, then t is the variable. Okay. So let's look at one example of a definite integral. I would like to find the integral from 0 to 4 of the function g of x with respect to x for this function, right? This is the function I'm integrating, and it's made up of a bunch of pieces of straight lines, right? Y equals g of x. And so I'm not even giving a formula, just a picture. So what does that definite integral mean? Well, it means the net area between that graph and the x-axis. That is the green and red areas there. But it's net, so that means I do the stuff above the x-axis minus the stuff below the x-axis. So that's the green stuff minus the red stuff. Well, those are all straight lines. I can find areas with straight lines pretty easily. So the positive area, the green part, is a rectangle from x equals 0 to 1, and then a right triangle from x equals 1 to 2. So there's the dimensions. Both of them are 1 wide and 2 high. So the areas are 2 plus 1, right? Length times width for the rectangle, 1/2 base times height for the triangle, and that adds up to 3. So the positive area, the green area there, is 3. The red area is an upside-down triangle. Its base is width 2, and its height is 2. And so its area is 1/2 times 2 times 2, which is 2. That means the definite integral is the net area. That is the positive stuff minus the negative area, the area above minus area below. So 3 minus 2 and that's 1. This definite integral equals 1. Okay. The question I want you to answer and bring to class tomorrow is to find this definite integral. The integral from 2 to 6 of f of x for the function that is just a horizontal line at y equals 3. All right, I will see you in class.